We're continuing on page 5 of the Chapter 10 AP Chemistry packet where we're talking about heat of vaporization. We found a relationship between vapor pressure and temperature of a liquid. We found that as you increase the temperature, the vapor pressure increases. This is the graph of that. These are the data points for the temperature and the vapor pressure. If you were to graph these numbers right here on the paper, you would find a curve. We're trying to turn it into a line to understand it better. The line will happen when you turn vapor pressure into Ln and 1 over temperature into 1 over temperature in Kelvin. We put them into our calculator, and we have the calculator generate all the numbers for these into our lists 3 and 4 in the previous video, and we found this to be the graph, which is a straight line, which is what we predict right here. The slope of this line is equal to negative HVAP over R of this substance. And so what we do is we use the calculator to find the slope. So we go to stat, as we did before. Stat, now you have to go to calc. You choose linear regression, and you have to tell it which list to do. Even though you just graph list 3 and 4, it's always over here going to do list 1 and 2 by default. And you don't want list 1 and 2, you want 3 and 4. So you go second function, list 3, comma, second function, list 4, and here is your data for your calculations. So we're going to copy down the A and the B. The A, the slope, was negative 19,038, and the B was 18.6. So that happens for our equation of our line. So now what we're going to do is we're going to use that information to find the slope and find the missing the HVAP from the slope and find the missing vapor pressure and temperature. So to find the HVAP, we're going to do slope equals negative HVAP over R. So that means that negative 19,038 equals negative HVAP over 8.31, and so HVAP is going to equal 158,206. Now that's in joules per mole. Probably want to change it into kilojoules. So 158 over here. Let's fix that. Okay, so we want to change it into kilojoules, so you can divide by 1,000, make it 3 sig figs. So that's going to be 158 kilojoules per mole. So what that means is it takes 158 kilojoules per mole to vaporize lithium. Okay, now what we're going to do is we're going to find the missing vapor pressures. So you have an A and a B value for a line, so you could always put it into the y equals ax plus b, and look at this is the temperature, which is the x value. Of course, you have to change it to Kelvin. So what you're going to find is this equation is going to go y equals ax plus b. The y is the ln of Vp, so that's what we don't know. The ln of Vp equals the slope. The slope, remember, was at negative 19,038, so negative 19,038. The temperature is 1 over Kelvin for the x value, but you have to change this into Celsius. Sorry, to Kelvin. So 1150 plus 273 will be your temperature, and then you're going to have your intercept, which is 18.6. So what you're going to have when you do all that math on the right is the ln of Vp equals 5.22. And then what you have to do is you have to take the inverse ln of 5.22. Okay, so you have to use the second function of ln of 5.22, and that will equal the vapor pressure, which is equal to 185, same unit as before, which was millimeters of mercury. And that's going to be your missing vapor pressure, 185. So that would go right here. Now let's take a look and see if that makes sense. 1150 as a temperature is between these two temperatures, and so you would expect that the vapor pressure would also be between these two, which makes sense. Okay, lastly, we have a vapor pressure of 800. So again, we're going to use our y equals ax plus b. So this time it's going to be the ln of 800 equals negative 19,038 times 1 over T. That'll be Kelvin, of course, 18.6. So you're going to find, when you do your math, that 1 over T equals 6.26 times 10 to the negative fourth. So that means that T equals 1598 Kelvin, which equals 1325 Celsius, if you wanted to get it back to Celsius for the chart. So let's fill that in, 1325 Celsius, 1325, and let's see if that makes sense. We know that 800 is basically right over here after 760, so you would expect 1325 to be after 1310, which it is, so that also makes sense. The last thing you need to find is the normal boiling point for lithium. That means the boiling point when the atmospheric pressure is 760. So what would happen is on your original graph, that would be over here. Okay, if this were 760, you would find where is the vapor pressure, what temperature is that vapor pressure, and that's going to be your boiling point. Because the vapor pressure, remember, has to match the atmospheric pressure when something boils. Well, that's not really going to help you because we don't really have an equation for the curvy graph. We have an equation for the straight graph. So we're going to have to use the straight graph to find the normal boiling point. So normal boiling point means that it's at 760 torr. So again, we're going to use our y equals ax plus b. Our b is 18.6. Our y is the ln of vapor pressure, which is going to be the ln of 760. The a is the negative 19,038. And then we're going to solve for the boiling point in, it's going to be in Kelvin in this one. So when we do that, we're going to have to plug that in to our calculators. I actually do not have that worked out already. So we're going to do that real quick. We're going to take the ln of 760, then we're going to subtract 18.6, and then we're going to divide that by negative 19,038. So we're going to get this to be 1 over temperature equals 6.29 times 10 to the minus fourth. So that means that T is the inverse of that. When you inverse that, you're going to get 1591. If you round it out to the nearest 1, that's Kelvin. And when you subtract 273, that comes out to be 1318 degrees Celsius. So that should be the normal boiling point. That's pretty high, which makes sense because you're trying to boil lithium, not melt, but boil it. Lithium's a metal, so to boil it, that's going to be over 1,000 degrees. Now let's take a look and see if that makes sense, and guess what? It's pretty close because in our data we actually had a 760 in the data, which usually will not happen if they ask you for the normal boiling point. And this is 1310, and within rounding, 1310 and 1318, this would round to 1320, and if you rounded this to 1320 within sig figs, that's going to be okay. So to find the normal boiling point, you just plug in the regular atmospheric pressure in the correct unit. If this had been in atmospheres, you'd want to put a 1 here. If this were in kilopascals, you'd put a 1 and 1.3. Torr in millimeters of mercury is 760, and you solve for the T, and that is the normal boiling point.